the loop yesterday when I showed you a formula for computing this sum. So yesterday, as an illustration, I showed you that this is really the same thing as writing this sum like that. And then I showed you some other, when I was illustrating the notation, I showed you some equivalent expressions of the same sum. And then we got to a formula for this. And I said in general that we looked at this expression. This is just summing those numbers from 1 to n. What we said is that this is going to be always n into n plus 1 over 2. And I gave you a good reason why that's true. I said if you reverse the sum and add it to itself, you'd have ended up with n copies of n plus 1. And that's why it's n times n plus 1. But you just added the number to itself, so that to get the original number, you need to half it. And that's why that's the formula. But what I just to confirm it, for those of you who still don't know what this means. In other words, you just look at that, those are just letters. They don't mean anything. Remember when we added this and you got 15, just to illustrate how this would work, you could plug it in. And based on this, you could then recognize that this would just be 5 into 6 over 2, which is 15. So in other words, it's just a confirmation that the formula is actually working. For those of you who are not so on such good speaking terms with mathematics, right? If algebra is not your friend, that might have been useful to you. Sorry to bore the rest of you who are wondering, why am I wasting your time? I soon give you something to hold on to. All right. But that was just to close the loop. So yesterday when I asked you, what's the sum of the first 100 numbers? 100 numbers from 1 to 100. Nobody, well, I know a few people knew the answer, but nobody was jumping up and down. How about today? What's the sum of all the numbers, integers from 1 to 100? Not quite. Well, you're on the right track. You're just doing arithmetic bad. 5050, right? 5050, yeah. Right? You see what you did wrong, right? Okay. That's not 11, that's 101 times 100 over 2. All right, so you get the idea. That's how you do that. Notice the big difference. When we discussed it yesterday, we said, how would you add up those numbers if you weren't thinking about it carefully? You'd say, well, if I had a computer, I could just write a loop, just add numbers from 1 to 100. But that would take 100 steps. That would take 100 additions. How many arithmetic operations does it take to do this? Not quite one. There's an addition here, there's a multiplication here, there's a division, 3. And it doesn't matter what the size of n is, sort of. Yes? So what you're seeing is tremendous power, right? You're going from something that depends on the value of n and scales proportionate to the value of n to something that takes the same amount of time no matter what the value of n is. That's a huge difference. It's that sort of difference that we're going to be examining over the course of the semester with different kinds of problems and different solutions for the same problems when we want to compare solutions. All right? So anyway, I'm using the opportunity to cover this background to illustrate to you the algorithmic techniques that we're going to focus on and how we're going to do our analysis. But the focus right now is actually just on the mathematics. So moving on. Oh, I did leave you with our problem yesterday. What's the sum of the first n odd numbers? N squared. Yeah, the answer is n squared. So if you tried it on your own and you got n squared, that's correct. We're gonna see how to solve that in a very systematic way in case that was not straightforward for you, because I gave you this formula, but I didn't give you a formula for, this was a question yesterday. What is that sum? And you might say, well, I don't know. That don't look like anything that I gave you. How am I expecting you to do that? All right, so I'm going to illustrate that for you shortly when I get here. Before I get there, though, I want to give you another tool to put in your toolbox. So these kinds of sums, summing terms that are uniformly spaced apart, because this is increasing by 1 each time. In this case, these sums are separate, spaced by 1. In this case, these terms are spaced by 2. If the spacing between the terms is a constant, then that's called an arithmetic series. Okay? So if you're solving an arithmetic series, this formula is going to come in handy. You can use this formula to resolve it. And I'm getting to that soon to show you explicitly how to do that. Before I do that, I want to show you how there's another kind of series called a geometric series that has also a nice systematic way to express its sum. So first of all, what is a geometric series? Let's examine what would be 1 plus 2 plus 4 plus 8 plus 16. Well, you should know this one by heart. You did computer organization? All right, yeah, it's okay. So, but let's examine, we're going to see how to get that. A series like that, where the terms, what's the relationship here? There's a constant ratio. So the successive term is a fixed multiple of the previous one, its predecessor. Okay? In this case, that ratio happens to be 2. So if you have a series sum like this, there is a nice formula for this. Now, if I wanted to write this down, I could write this as, using our notation, this is the sum. In this case, what I want, since the ratio is 2, I'm multiplying by 2 each time. So as I increases, the next term is going to look like, each term looks like 2 raised to the i power, right? Because the next one is 2 times the previous one. So it's an extra multiple of 2 on each term. But if I write my term as 2 to the I, where do I start? Because the first term is 1. So 2 to the 0 is 1. So in this case, it's starting from 0. And where does it stop? Yeah, the last term was a 4. Right. So now there's a generic formula that I want you to also know by heart. Just like how I'm asking you to learn this one, you can dream it. For geometric series, so that's what this is. So in this case, we're going to have R is a constant, and that constant, the only constraint on it is that it can't be 1. So in this example, that R was representing that this instance here, R is 2. But in general, if I start from 0 and I go up to an nth term, and what I'm summing is some constant ratio R raised to that power, the final answer is going to be the ratio raised to the next power minus 1 divided by ratio minus 1. There's an easy way to see that. I won't bother to try and prove it, write down the proof, but I can speak it for those of you who can follow it. If you were to imagine, you want to see it, or don't waste your time? Sorry? Okay, so suppose I, okay, so let me write it down. Let me sketch it. All right, so suppose I call this sum S. Hopefully you can, when you see this, you won't forget it. You notice that if I were to, so let's write this out. That is, S is really 1 plus R squared plus all the way up to R to the n. Yes? If I were to multiply everything by R, what would happen? It's kind of like I get a shift. Because the R times 1 gives you R. R times R will give you R squared. And the last term would be r to the n plus 1. Agreed? Say yes. Now, if I subtract these two, I'm going to cancel out all the middle terms. The only ones left will be the 1 up there and the r to the n plus 1 over here. You agree? So what you see is, so rs minus s is r to the n plus 1 minus 1. And that means that s is r to the n plus 1 minus 1 over r minus 1. You're asking me a question? Oh. Okay? That clear? All right, so if you were to plug it in here, what do we see? We can use that as our example. The sum from I equals 0 to 4 of 2 to the I, according to this formula, would be 2 to the 5 minus 1 over 2 minus 1. You notice that when r is 1, when r is 2, 2 minus 1 is 1. So that denominator kind of goes away. Right? Yeah. All right, so this is, you've seen this before. This is not new to you. But maybe you didn't see why, I don't know. I hope this was useful. All right. I don't really care how you got to it, how you saw it before, whether you've seen it before. You've seen it now. I know you need to know it. All right, so now you're responsible for this. Like I said, I'm giving this to you on day 1 because you'll be amazed how many times this comes up. And if I could bet money that when the time for the tutorial comes and this part of the problem that requires this knowledge comes up, I can bet money that not everybody's going to have the answer. And then when I write it on the board, I go, oh, that's, yeah. Anyway, I hope it sticks this time. All right. Any questions? So let me return to this question here. What if you have slightly more general expressions that you need to compute your sums for? You know, in real life, when you do an analysis, say on a piece of code, what we're going to be doing is counting operations. You're going to be examining what would happen on a particular input. You're going to be trying to assess the number of times something happens. And when you're doing that count, what you'll sometimes recognize is, okay, so the total cost of running some code is going to be the sum of some things. For example, if you have a loop, then you'll be, for every pass through the loop, you're adding the work done in each pass. And so the number of iterations might be the number up top, and the term is going to be how much work is done on each pass. So these series sums come up all the time. Naturally, just like in any real life situation, what comes up in real life often is very different from what you see in this very abstract model. So we want a few more tools to be able to deal with what is likely to come up. And namely, this is a simple example. This doesn't look like this, so I can't use that formula directly, not to solve this immediately. But maybe I can perform some transformations. And in fact, I can. So there's this property called linearity. In general, we say that a function is linear and in this case, it's really an operation. All right, let me call it an operation. I think if I waste time trying to write a nice definition, it would probably be lost and no point. Let me just write down what is true. All right, so for constants, if A is a constant and any function f the following are true. I'm going to give you a bunch of things. So if I were to sum A times f of I, it doesn't really matter where I start. I gotta use some different names. So let me say I'm gonna go from some arbitrary A to some arbitrary B. C is a constant. F is any arbitrary expression, any function. It is true that if you sum between the same limits, same start point, same end point, what's the difference here? In this case, you're scaling these terms by C. What happens here? You're summing it first and then scaling it. That's just a distributive law, right? Here's another one. I beg your pardon? Homogeneity. I know about homogeneity for differential equations. What do you mean for this? What does? You think of differential equations? I'm asking. For differential equations, those terms make sense and they have something to do with what the right-hand side is a function of in terms of the independent variable. But we're not talking about that. A different story. But this is just straightforward. If you're summing two separate functions, and these are your terms, and you want the sum of all of them, it wouldn't matter if you were to sum the f's first and the g's separately and then add the sums. You get that? Because addition is commutative, right? So this is the same as long as you keep the limits the same, the range, the endpoints. Okay? Sometimes the second one might be called separation of terms, if you want a name for it. But it's just dependent. I mean, it's true because addition is commutative. You can do addition in any order. The first one is true because because multiplication distributes over addition. But how is this useful to us? You see, this now is a very powerful tool because if you need to solve this problem, it means that we can apply both rules to this. Yeah? So watch. So the sum starting from, so I start from 1 to n of 2i minus 1. That's the sum of those odd numbers, right? First n odd numbers. According to the second rule, I could look at this as this is the f of I, and minus 1 is my g of I, yes? So then this is the same as the sum from I equal 1 to n of 2i and plus the sum from I equal 1 to n of negative 1. Agreed? Okay, and then I can use the first rule to get this. So that's the same as 2 times the sum from I equal 1 to n of I. And there's a plus the sum from I equal 1 to n of -1. Any questions? I'm going very slowly today, so those of you who are wondering, what kind of course is this? It's not as Mickey Mouse as it looks. I will step it up soon enough. But I just want to make sure everybody's on the same page. All right. Now we'll have a formula for this, don't we? So the formula right there. So this we can then substitute. So this is 2 times. Now this sum, if you're just summing those i's, you'd have gotten n into n plus 1 over 2. And that's going to be multiplied by 2. What's this though? Negative n. Why? Is -1 added to itself n times. So that's negative n. And then if I were to simplify, well, this is going to give me n squared plus n. And there's a negative n out there. So those go away and get a clean n squared. Okay? You knew that before, right? If you had 1 plus 3, you get 4. That's a square. 1 plus 3 plus 5, that's 9. That's another perfect square. 1 plus 3 plus 5 plus 7, 16. That's another perfect square, and so on. Another way to see that is that difference of 2 consecutive squares is going to be that odd number. That specific odd number. All right. Any questions? You're doing well. Yes. Which 2? This one, eat it. It got cancelled. All right. Let's do big. Well, no. Never mind. So any questions? No questions? All right. Let's move on to the next topic. How many people have seen logarithms before? High school? Maybe? I guess you'd have seen it in 1210? If you had to do, which calculus? Discrete math, you just saw it in discrete math? But maybe not everybody did discrete math. All right. I don't even think that logarithms are any particular mystery. So, you know how we say the inverse of addition is subtraction? And the reason we say that is that if I start with a number A and I add a B to it, if I wanted to undo that add B, I'd subtract B. Yes? Okay. So the logarithm is just inverse to exponentiation. So if I've already, say, for example, raised 2 to the 3rd power to get 8, that's I exponentiated 2 to the 3rd power to get 8. If I wanted to undo that, I need to take the logarithm of 8 base 2. Get that? So the log of 8 base 2 is 3 because 2 raised to the 3rd power is 8. That's how you want to think about it. Okay? So the logarithm of a value is the power that you'd have to raise the base to get the thing you just took the log of. Okay? Sorry? So I'm wasting your time? Oh. I'm just giving you a hard time. All right, so there's a nice solid definition for you. Let's work with a few properties of the log, all coming from this definition. So in this setup, I'm going to use b. Must understand that it's not 1. I'm going to refer to x and y. Both of those must be positive because the log of 0 doesn't exist. And I guess I'm going to have a point at which I might refer to it. A and a c, it might be constants when I get there. All right. So first of all, the definition itself gives us a very important property. If you take the base and raise it to the logarithm, by definition, you get what? You get x. By the way, on the topic of notation, I want to point out something to you. Because I have lines on the board, you might be confused. I see some students do this, and then I realize when you start writing that, no wonder you get confused about what logarithm is. This is not b raised to the x power, okay? That b is a subscript. The x is on the same line as the log, okay? It's not the log of b to the x. If you write that, if that's what you're thinking, you'll be totally lost, and I won't be able to recover you. Okay, and at the end of the semester, you'll still be writing nonsense. Whenever you see the log, you're going to run screaming for the hills, and you'll get none of those marks that I'm giving away to you. But if you remember that b is just a notation to say this is the base that, with respect to which I'm working. And what I want is, I want to find out what is the power I needed to raise b2 to get x. Okay, so it's just a notational thing. I know you're confused, it's not b raised to the x. All right, so when you raise b to that number, you get x by definition. All right, it also means that, so I want to introduce my a now. If I take well, let me not do that yet. If I take the log of a product, this is equal to the sum of the logs. You don't see that? Not so sure that's why that's true? Not obvious? All right. No, you don't just accept it. What? All right, let me ask you this. So, what this is really saying is that if you were to raise b to this power, you're supposed to get xy. Right? That's what that's saying. Because that's what log means. Well, all right. So if you raise b to this power, remember indices, when you have sums in the indices, what does that mean? Now you take the product of the expressions, right? So b raised to this right-hand side is really the same as b to the log x base b times b to the log y base b. Because the plus is in the index now. And b to the log x base b is x. And b to the log y base b will be y. So then b raised to this will be x times y, which is what's there. Then try it at home. Recommended. If you don't see what I just said, try it at home and see. You're going to need to recall your indices. Likewise, though, this kind of next property is a corollary of this. If I have Let me just introduce an a. So a is an integer. Then the log, actually it doesn't have to be, it's any real number. Let's just work with that. It's easier to argue when it's an integer, but it's true for real. The log base b of x raised to a power is just that power times the log. Why is that true? Well, look, if you buy the second one, even if you didn't see why it was true, if you buy this, then you recognize that x to the a is just x times itself 8 times. And therefore, the log of that repeated product is going to be this repeated sum of those logs. So you add log x base b to itself 8 times, you're going to get 8 times log x base b. Okay? So this one follows from that. Because division is just the inverse of multiplication. In other words, dividing by a y is the same as multiplying by the reciprocal of y. Then in fact, this property, you can use the same rules for division. So if it were x over y, it would have been log x base b plus the log of 1 over y base b. And the log of 1 over y base b is what? Is a negative of the log of y. Why is that? Because 1 over y is the same as y raised to the minus 1 power, right? And then you can look at it like this and say, oh, so log of y to the minus 1 would be negative 1 times the log of y. Okay? So the upshot of what I just said, this is not a separate property, it's a corollary of this. This is the same as the log of x base b minus log of y base b. But that's not a new rule. That comes from this. All right. Time to show you. I have 2 more. In our context, we're going to use 2 as our base more often than not. Only because we'll often be doing things like dividing something by 2 over and over and over again. And we're going to have to ask ourselves, how many times can I divide this thing by 2 before it whittles down to nothing, or to 1, or something like that? And that's really asking the question, what power of 2 do I need to overtake the value I started with? If you think about it. Because a power of 2 represents how many times I have to divide that, repeatedly divide by 2 to eventually reduce it to 1. So we're going to be using this, that's where the logarithm is going to come in. Because any process that repeatedly divides by a constant, the number of divisions needed before the value that you started with gets reduced to something less than or equal to 1 is going to be proportional to the logarithm of the value you started with respect to the base of the value you're dividing by. So that's why it's going to come up. Now, therefore, we're going to be asking what's the log of something base 2. If you have your calculators, by the way, yeah, if you have a calculator on you, or if you've looked at one recently, you might notice that there was no log base 2 key. There was natural log, which is log base e, and you might have a log base 10. That's usually there. But there's no log base 2. Suppose you are in, well, it's not pertinent to this course because you can't use the exams in exams for this course anyway. You can't use the calculators in the exams for this course. But because you don't need it. But suppose that you are actually trying to calculate the log of something base 2, whether in a function in a program that you're writing, or maybe in an exam for a different course. maybe in some networking course or some computer architecture course or something. How would you do it? Sorry? Yeah. So we need a rule to change base, right? Now it happens that the following is true. So I'm going to introduce C as another base. So obviously for it to be a legal base, it can be 1. So if I wanted to find out what is the log of x base C, but the only tool I have is something that can calculate logs base B, some B, like E, for example, or 10. Then it turns out that this is equal to the log of x base B divided by the log of C base B. Now that's going to come in, so you can use that practically to compute logs that you don't have the keys for on your calculator. But more pertinent to us, you're going to see that when later on we start contemplating this idea of how much time is taken or how many iterations are needed, and we recognize it being log-based something, you're going to see situations where, because we've already established that we don't care what the constant is, there's a constant multiplier somewhere where we're ignoring it. When we get to orders of growth, you'll see that. That means that the log of a number, regardless of the base, differs from the other logs with respect to other bases only by a constant. Let me say it a better way. If I wanted to find, suppose you're arguing with me over what the base should be. I'm saying, okay, what's the log of 1,000,000? And you say, well, base what? Base 10, it's 6. Base 2, it's something more than 20. Between 20 and 21, or thereabouts. So you might say, well, so the base matters, because 6 and 20 are not the same numbers. But if I'm interested in the pattern, in terms of how much more, how does this function grow as I put in bigger and bigger values of x, this formula tells you that the relationship between whether I'm working base 10 or base 2 is only going to change by the ratio of this constant here. The constant being the log of 10 base 2, if I'm working with C being 10 and B being 2. So in other words, that answer that you get because you change the base is going to essentially be a scaled version of the original answer you would have gotten if you used a different base. It's going to be by a constant. And that's what is going to allow us later on, when we're not interested in constants, to not care about the base. But that will come later. It's this, for now, I want you to pay attention to this because this is the property that you need to hold on to. All right, one more. Yes? Go about what? Why it's important? No, man. That was just to motivate you to learn it. Right now, I just want you to focus on learning it. Yeah, right now, how it's going to get applied and how you're going to use it, I'm kind of getting ahead of myself because when we talk about orders of growth, you're going to see that we're going to suppress some constants. I'm just explaining to you here. For now, here's what I want to pay attention to. Notice that log x base C, log x base B are almost equal to each other. There's a constant because B and C are fixed numbers. So log of C base B is a fixed, some constant. We don't know what it is, but it's something. But the only difference between these two is that one is this constant times the other. That's what I wanted you to pay attention to at this point. That's all I needed to grasp for now. Okay? Last one. This one is kind of neat and interesting and surprising if it's the first time you've seen it. That one just looks like that should be wrong. But I'll leave it as an exercise for you to. Yeah, x raised to the log y base b is the same as raising y to the log of x base b. You're trying to reason out why it's true? Do you see why it is true? You do? You reason out algebraically why it's true? Not just with some numbers. Just plugging in numbers doesn't tell you anything. It just says by buck-ups, maybe that set of numbers work. But what you want to do is algebraically convince yourself that this is actually true for all x and y. So I can leave it to, I'll give you something to work on, chew on that while I'm still cooking your POTW0, because I have a little glitch on that. Hopefully tonight it will pop, but I'll give you something to think about to prove this. Question? Is that a question at the back? No. No, I don't have any mechanism for marking. You get brownie points. All right, any questions on logs? You certainly don't sound settled. Okay, so I actually got to what I was planning to do for today ahead of time. So no point wasting time. I can start next topic, don't it? All right. So orders of growth. You guys have seen orders of growth before in discrete maths, right? Right. So here's what I want you to, I want you to bear in mind a few things. We're going to be using these notations, big O, theta, omega. You've seen formal definitions for them before. The definition I'm going to show you, I don't know if that's the one you've seen. I'm going to give you one that helps you operationalize it so that you can work with it rather than just simply understand about existence of things. All right, so I'm going to try and motivate this a little bit for you. If I ask you if x and y are numbers, you recognize that you could compare them. You could, it's a valid question to ask you, is x less than y or not? Right? If x is 5 and y is 7, then x is less than y, yes. But what if you have functions? Suppose I have a function suppose I want to compare functions. Suppose that this is a variable, let's say this is a variable n. This might be some count of something. This is, I'm going to say it's a number of steps or something. It's an integer. And I have two separate functions that tell me how many steps are needed for a given n, for example. So the first function might look something like this. Let's call that one f. And I have another function that looks like this. This one is going to be G. And now I ask you, which function is bigger? Is it actually a sensible question? Not really, because you see, bigger where? Because if you're talking about before this point, let me drop a little label on this. Call that an N0. If you're talking about before N0, well, G of N is less than F of N over there. And that's just because my two functions are so easy to draw. You could have a function that wiggles about the place, and then it's not even easy to describe where it's less than and where it's bigger. Yes? But you can see that, well, as N gets larger and larger, though, then G is kind of growing off to infinity. Well, both of them going to infinity, but G is growing there faster. So if I were to ask you which one is bigger as N gets larger, that's a well-formed question, and that you can answer. So what orders of growth are about, or this asymptotic analysis, is really a notation for documenting how functions grow as the input size grows. All right? And we have 3, in fact, there are 5, but there are 3 that we're going to worry about. And they have rough equivalences to the numerical comparisons. So I want you to think so here's the asymptotic comparison, and here's the numerical analogy. So if I say that F of N is big O, G of N, that's like saying all right, so let me say it like this. The numerical analogy is to less than or equal to. And the way we're going to say this is that F is not growing any faster than G. And sometimes in maths they'll say this phrase up to constant. And you'll see why, because this big O, tomorrow when I show you the form, not tomorrow, Friday when I show you the formal thing, there's a, you know, so rub out the F of N is less or equal to G of N, because technically speaking, you're allowed to scale the G. So what it really means is that F is less than any constant times G once you keep that constant fixed, the constant. All right. If I write F of N is omega G, then the analogy I want to keep in mind is greater than or equal to. If both of these are true, then we're going to write F of N is theta G, and analogy is equivalent. And then we have 2 that we don't talk about too much in this class, but since I'm on the topic and I'm just at this point very crudely doing it, if I were to write F of N is little o of G, then that's like strictly less than. In other words, F of N is growing much slower than G. And if I were to write F of N is little omega of G, then that's like strictly greater than. One way to look at that is, no matter what constant you choose, if you were to examine, in other words, you could slow down the G as small as you wish, it eventually would exceed F of N, no matter what. Essentially, and you'll see tomorrow, Friday when I show you, we're going to talk about this in terms of limits. And you can see that what this really the little means the limit of the ratio of fn to g of n goes to 0. Whereas in this case, when it's a little omega, it goes to infinity. Okay? But you're going to see that all these nice properties that tend to hold, you know, like you might think, well, less or equal is like a union of those things, less than and equivalent. That kind of thing is going to hold as well when we're dealing with the formal definitions of these. But that's for Friday, and I'll see you then. Very quick meeting. I don't think the text is there, so if you just pan the camera over to get a good picture of it. You can probably just pick up the camera and just hold it steady on the right side. So that somebody can, if they're taking notes, you can. And a quick meeting.